Hello, today we're gonna talk about sheaves on a basis, and we'll start to define the structure sheaf of the spectrum of a ring. So let's take F to be a sheaf on a basis of a topological space. So this basis B is a basis of a topological space X. And what I mean by a sheaf on the basis is we have a sheaf which is only defined on sets of the basis, so on sets in B, and we check the sheaf axioms also only on B. So what I mean is we check the sheaf axioms for U, some union of Ui, where U is in the basis and also the UIs are in the basis. Okay, now we want to define a sheaf on the whole space. So let's take some V and X open. So X is our topological space and not necessarily in the basis. And we define, let's call it F prime of V. So that's a new sheaf, and that's the projective limit over the open sets in V which are in the basis, then f of u. So let me spell it out what this projective limit is. So we have some tuples, so let's call them SU, and this is in the product of the subsets of V that are in the basis, and then f of u, and we have some condition, namely that SU, let's call it SU restricted to U prime is equal to SU prime for all subsets U prime in U. So if we have some subsets, and then the restriction should be this element. So this SU prime. So this is some compatibility condition. Okay, and I claim that this is a sheaf, so let's check at least the first sheaf axiom. So let's look at the claim. So we'll just check the first one. The second one is similar. So let's take some... Oh, let me first tell you what the transition maps are. So let's say we have... let me tell it right now. So let's say we have W in V, and then we have F prime of V to F prime of W. And so this is actually quite straightforward. So we have here SU, and let's say this maps to some S, let's call them U twiddle, but basically it's the same as. So here, let me tell you what I mean with this U twiddle. So we have here, we go over the U in V, U in B, and here we go over the U twiddle in W and also basis elements. And so we just have a smaller index set here, smaller than here, but the same elements. So why does this work? Well, we go all subsets of W are also subsets of V, so that works, and that's our transition map. Okay, now let's check the claim that this is a sheaf. As I mentioned, we check it just for the first one, so let's take some open covering of V, so open cover, and let's take S and T to be in this F prime of V. And now let's look at the restrictions. So we have, let's see, so we have S restricted to VI is, or well, S, so this is some SU, and this is as before some S, let's call it UI twiddle UI, so where UI twiddle is a subset of VI, which of course is in V, and also the UI twiddle should be basis elements. Okay, and similarly for the T, so for T, and okay, so let's see. So if S restricted to VI is equal to T restricted to VI for all I in the index set, then this means that S UI twiddle is equal to T UI twiddle, so for all I in the index set and also for all UI twiddle. So again with, well, let me just spell it out. Okay, so for all these sets it's true, and now we know that this holds for all these UI twiddle, and therefore by being a sheaf on a basis, it also holds for this for S and T. So namely what I want to say, so these SU and TU are defined on a basis, and now we have some covers of these U's, so namely we can cover these U's just as U intersection with I in I and union over the UI twiddle. And then by being a sheaf on the basis, all these SUs agree with the TUs, which means that S is equal to T. Okay, that's about this. So we have the first sheaf axiom, and you can check the second one similarly. And let me also tell you, so let's take some V in the basis, and then we get that f prime of V is isomorphic to f of V, and this isomorphism is also functorial, so we have, so let's say we also have f prime of W isomorphic to f of W, and then, so we have maps between them, and these maps commute. That's what I mean with functorial. And so what does this do? So 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 this SUU maps to SV, so for these being in here. And well, why does this give an isomorphism? Well, we have that these are defined by, so if we restrict SV restricted to U, then that's just SU. So these SU are determined by SV, and so we get also a map in the other direction, which is inverse to the first one. And then we have this isomorphism. And this isomorphism also tells us that if we think about it more in terms of categories, that if we get an essentially surjective functor, so from sheaves on bases to sheaves. So why is that? So essentially surjective means that for all we take a sheaf, and then we can construct one in the image of the functor, which is isomorphic to the given one. And so here, well, it's rather in the other direction. So we have we are given a sheaf on a basis, and then we construct this sheaf, and then by restricting to the basis again, we get a sheaf on the basis, which is isomorphic again to to the one we started with. So we get it as essentially surjective, and then one can check that it's also a fully faithful functor. So we get an equivalence of categories if you want to think about it in these terms, and so in terms of category theory, but we didn't check fully faithful, but it's not, so we already have the maps also in between these, so the transition map, so it's should be okay to check. That shouldn't be too hard. And so this means us that we can basically think in terms of sheaves or in sheaves on a basis, and both are isomorphic. So a sheaf is isomorphic to another sheaf if and only if the corresponding sheaf on a basis is isomorphic to another sheaf to the corresponding second sheaf on a basis. So what I mean, let me write it. So A is isomorphic to B if and only if F, so F is not a functor, is isomorphic to f of b. Okay, so let's start to define the structure sheaf of a scheme, or of, not of a scheme, of an affine scheme. So let's take a ring and X to be the spectrum of the ring. Okay, and now define the structure sheaf on X, which we call OX, on, well, we define it on the basis, and well, no, let me tell you which basis. So we have these principal open subsets for F and A, and we'll define it on this basis, and we've already seen that that's enough, so we get a sheaf on the space X on the spectrum, and namely we define it as OX of dF to be the localization at F inverse. Okay, that's how we define it. Of course, we still have to check that that gives us a sheaf. So let me first tell you about the restriction maps, and probably we'll check in the next video that it's a sheaf. So let's take some set in here, and now we want a restriction map. Okay, so how do we get it? So let's see. Let's look at something we've seen last time again. So we have an induced map by the localization to the spectrum of A. And we've seen that the image of this is d of f. So the image of phi is d of f. Now let's look at this map. And we get a map psi, and the image is d of g. Okay, but now this A, so the image of psi is d of g, and of phi, of course, it's d of f. And we've seen in the last video, or was it the last one? But let me check, it should be somewhere. No, it wasn't the last one. So where are we? Yeah, exactly. So we had that the A algebra, the A localization at F inverse is initial among all A algebras such that the induced map factors over dF. Okay, now we have this A algebra, and we want to look, does this map psi, so where do we have it? See, so we have this map psi, and we want to know, well, does it map over dF? But of course it does map over dF, because we have that the image is d of g, so which is a subset of dF, so it factors, which tells us that we get a morphism from actually so we get this morphism by the universal property from the localization here to the localization here. And well, actually we would have also a commuting diagram with A, but let's not worry about this. So it's actually not just a morphism, but it's a unique morphism, which, well, then let me write it. So that's the unique one, which makes this diagram commute. And so we have here now, let me write it out so that you see it. So we have OX dF, which is this localization, and then we have Ox d of g, which is this one, and we get the required restriction map. Okay, so we have the restriction map, and next time we'll check that it's a sheaf. And probably at some point I'll make some interlude to give you some more motivation. So to give you some more motivation in terms of Riemann surfaces. So probably I'll make a short video about Riemann surfaces, but that won't be too detailed, just to give you some connections to algebraic geometry. And also we'll have to deal a little bit more with sheaves, so we'll have to see what the stalk of a sheaf is and stuff like that. And probably we'll also need sheafification. And so that's all on the to-do list. Let's see how we go about it. But these are all things that we'll probably see. So thanks for watching. Have a good day and bye.